All right, in this video, we are going to talk about a type of enzymes called allosteric enzymes. When we looked at Michaelis-Menten enzymes, we saw that we got this hyperbolic shaped pathway, shown in the blue here. And we remember when we talked about Michaelis-Menten enzymes, we talked about this. We talked about the idea that the enzyme plus the substrate had to come together to give us that enzyme substrate complex. And then that complex could break apart into the enzyme plus the product. And we didn't always show this double arrow necessarily because we were generally talking about right at the beginning, the initial velocity, initial rate. And so at the initial rate, we have so little product that we don't have a reverse reaction generally. All right, but this was the idea behind this Michaelis-Menten enzyme, that the rate of the reaction is only dependent essentially on how these things come together and then how they turn over to make the product. Sometimes when we plot the substrate concentration versus reaction velocity or reaction rate, we get a different shape plot. We get this sigmoidal shape instead of the hyperbolic. Write in hyperbolic just to have it all in one slide. Okay, so sometimes we get this sigmoidal shape. And remember what we would have here is we would have kept the enzyme concentration constant, varied the substrate concentration, measured the velocity. So at each substrate concentration, how fast is the reaction going? New substrate concentration, how fast is the reaction going? And we've plotted this. And now we see this sigmoidal shape plot. And this indicates to us that something else is going on beyond just this simple Michaelis-Menten idea of rate being dependent upon the formation and breakdown of that enzyme substrate complex. It turns out that allosteric enzymes still work. We're still thinking about this basic idea of how an enzyme works, but they are also information sensors. And it turns out that what's happening is that there are other structural changes in the enzyme that affect the activity of the enzyme. So this affects the activity of the enzyme, but there are other structural changes that also affect it. So velocity is dependent upon something besides just the substrate concentration. Okay? So allosteric enzymes can be regulated by products. So this is one kind of option or one example. So if we look here, we would have substrate A go into substrate B, and it's got some enzyme that helps it do that. Product B. Product B becomes the substrate for the next reaction, becomes product C, we have a different enzyme, and so on and so forth. And in this case, we had 5 steps. We get to our final product F. In this case, there's only one reaction pathway all the way through here, so we might call this first one the committed step, because once this occurs, there's nowhere else for B to go. It's just got to continue down the line to get to F. So generally, if we have a committed step, oftentimes what controls that is an allosteric enzyme. And maybe these other ones are all Michaelis-Menten enzymes, but that allosteric enzyme, because they're a secondary pathway to controlling it, can help us determine, hey, do we want this reaction to happen a lot right now in our bodies? Do we want it to happen just a little bit? So it provides more regulatory control. So one example of this regulation would be feedback inhibition, where in this particular case, maybe the amount of product F comes back and binds somewhere on this first enzyme, this allosteric enzyme. And when it does that, it changes the structural conformation. It changes the shape and then slows or limits the activity of that enzyme so that And you can think about why that would work, right? If we are building this up, we must not need as much of this as we're making. So why do we want to waste our body's energy and everything making more of it? And so by having excess come back, bind to this enzyme, and slow this enzyme down, we can slow this whole process. So this is just one example, this feedback inhibition of how allosteric enzymes might be controlled by something other than just the concentration of the substrate. All right, so let's really think about why the shape of these curves are different. What story does that tell us? So as we look at a Michaelis-Menten enzyme, it is essentially, we always assume we have a certain amount of the enzyme, and once we start adding substrate, it gets faster and faster and faster until we've maxed out our enzyme amount, right? And then it doesn't matter if we add more substrate, we don't have any more enzyme. But the shape of the allosteric enzyme tells us something else is going on. There are many mechanisms to control these allosteric enzymes, so they can be controlled by their own substrates. They can be controlled like by another molecule, like in that previous example where that product F came back and controlled it. In general, most allosteric enzymes, and definitely in the case of one that has its own substrate controlling it, where S, concentration of S would be controlling this enzyme, it generally has quaternary structure, so it has more than one subunit. And when the subunit bonds to one active site, there's structural changes that affect the bonding at the other active sites and make it either easier or harder for that substrate to bond in the other active sites. You can have, in the case of some other molecule, not the substrate, controlling the allosteric enzyme, you could have an enzyme with just a single subunit, but it would have to have at least multiple binding sites. But definitely ones with quaternary structure are much more common. All right, let's take a look. Oh, and just kind of some of this in words. So allosteric means other shape. And so allosteric proteins are ones which subtle changes at one site affect the structure. And really in biochem, we're looking at the structure-function relationship, how the structure, the chemical structure, affects the function of the molecule, affect the structure and function at another site. So most common again with quaternary structure, we call this cooperativity. We'll use that term more a little bit later. And so we can have positive or negative cooperativity, where something either positively makes it that enzyme work faster, or negative, where it works a little slower. Okay, let's look at one model for how allosteric enzymes might work. This is called the concerted model. It's one of the simplest models for allosteric enzymes. And let's come over here and let's look. This is like our key here for what all our shapes mean. So we have essentially two different structural forms. This is an enzyme that has 4 subunits, so it has quaternary structure. Doesn't have to have 4 subunits. That just randomly, that's what we've picked for this one. So it has 4 different subunits. And we see that there are 2 forms. There's this T form. T stands for tense. And this is the inactive form. Or they can exist in the R form, which stands for relaxed. And this is the active form of the enzyme. And we've shown the T form with the squares, we've shown the R form with the circles. And if we look over here at box A, picture, our sample in like a big beaker, right? Here's our sample, and what we see is, wow, there's a whole lot more of that T form. So we're going to have some equilibrium between the T form and the R form. But what we see is that the tense form is more thermodynamically stable, that in the absence of any substrate, So there's no substrate here. We've just got the enzyme. In the absence of any substrate, we're going to have a lot more of the T form. It's not going to be active. But then we start adding substrate. And let's look over here now in this new beaker with the substrate added. And the substrate are shown, enzyme subunits that have substrate bonded are shown in that bright pink. So we're looking like here and here. All right, think back to your Gen Chem. Our equilibrium was between the T and the R state. And actually, let's draw this one right, much bigger, right, because it tends back towards the T state. These are the unbound enzymes. Our equilibrium is between those unbound enzymes. So y'all, when I bond substrate to this, I'm essentially pulling out the product. I now have less of this unbound R form. So if you think back to Le Chatelier's principle, if we start decreasing the amount of this, we start shifting our equilibrium to the right. So I had some of these molecules that were unbound, they bound the substrate, and now we're not counting those anymore in our equilibrium. So our equilibrium starts shifting more and more to the right and makes more. So see in this one, I have 3 of those relaxed state molecules. 2 of them aren't going to count in my equilibrium because they already have a substrate bound. In the concerted model, all subunits are either in the T form or in the R form. There's no intermediate. So once one changes, and we'll look at how this would happen, but some small change in the structure will kind of come through. It'll affect the hydrogen bonding, the hydrophobic effects. It affects all of those and changes all of the subunits to the R form. Well, now if we think about what would happen next, when we come down here to C, once that happens, those other subunits are more readily available for bonding. They're easier for the substrate to bond to. So we start seeing some of these enzymes that have multiple substrates bound to different subunits. And as we bind more and more of these, we see more of our T form switch to our R form. And as we bind more and more of them, that becomes kind of this exponential. And we really start to see lots and lots of the R form and very little of the T form. So in biochemistry, again, we're looking at that structure-function relationship. And so in this case, we're looking at how the structure of the T form changes to the R form, the less active form to the more active form, the one that is easier for those substrates to bond and activate. All right. So allosteric enzymes will always have more than one structure, and the structure will change when the substrate binds or when some other effector binds, and we'll look at an example of that. All right, these next 2 slides are really just what we talked through, but in words, so that if you like to read it, you can come back and take a look, right? Let's run through them real fast, just as a second review. So allosteric enzymes generally display quaternary structure, multiple active sites, and regulatory sites. One model that we just looked at is that concerted model. Features of that model. We have 2 different quaternary structures, either the tense state or the relaxed state. They're in equilibrium. Tense state is the more stable one when no substrate's present. R state is enzymatically more active than the T state. And all those active sites have to be in the same state. When we looked up here, we didn't have any that were like 2 squares and 2 circles. They're either all in the tense state or all in the relaxed state. Once we bind the substrate to one active site, it traps all the other active sites in the R state. And so it pulls some of the unbound R from our equilibrium. Le Chatelier's principle says, wow, then my equilibrium will make more of that unbound R, so it's available for bonding. I covered up some of the text here, didn't I? So allosteric enzymes are more sensitive to changes in the substrate concentration. So clearly there should be, finish my word there, in the substrate concentration near their Km values. So let's take a look at that real quick. If you remember, Km, the Michaelis-Menten constant, a little weird we're talking about that with allosteric enzymes, but we'll look at why, was numerically equal to the substrate concentration at half the maximum velocity. And we know that once we get that the enzyme activity will be high once the substrate concentration is above that Km. We see a lot of enzyme activity at a high reaction rate. If we look at that same Km constant for the allosteric, so still looking at the substrate concentration at half max velocity, we can see that that local substrate concentration, right, as I change the substrate concentration down here, it definitely has an effect on that velocity. And because of that, we still talk about Km and maximum velocity with allosteric enzymes. We kind of use those terminologies sometimes to describe those enzymes. It turns out that that Km value tends to be about the substrate concentrations we have in vivo, and so they're kind of it's important to know how a enzyme would react around those substrate concentrations. All right, let's take a look at the effect of regulators, and so we're going to look at a specific enzyme. This is aspartate transcarbamylase. So we would keep the concentration of that enzyme constant, and we would change the concentration of the substrate, the aspartate, and we'll measure the rate of formation of our product. And so the black line here is our allosteric enzyme with no effectors. So we have the enzyme, we start adding some of our aspartate, and we see this, and I know it's an allosteric enzyme because I get that sigmoidal shaped plot. But now it turns out that there are these other effectors, okay, CTP, ATP, that affect how well this or how fast this enzyme works. We can see that when we add ATP, it speeds up, right? We need lower substrate concentrations to get the same velocity. So this one would be a positive effector. So when we add ATP, it is somehow going to bond to our enzyme and cause a conformation change, a shape change that makes it easier for this reaction or for this enzyme to either bond to the substrate to facilitate that formation of the product when that substrate bonds. On the other hand, we see over here in pink that it takes a lot more substrate to get the same velocity, right? This is a negative effector. It's slowing it down. So if you think about, we still are going to have our T to R, so tent state versus R state equilibrium. And so really we think about how these effectors work by thinking about which state our enzyme would more likely be in. A negative effector will shift our equilibrium back towards that tense state, right? Less likely to react. A positive effector will shift our equilibrium back towards that R state, more likely to bond and react. Okay, when we added more, just looking at the black, right, when we add more substrate, we see that it shifts our reaction towards the R state because we see that the reaction rate goes up. So allosteric enzymes can control the rate of reaction based on what's in the cell. So not just the substrate, but other things that are in the cell. All right, and this is kind of just, again, the words of what we just did. We added a couple terms, so you can read through this, but when the disruption of that equilibrium is caused by the substrate, when the substrate is controlling how fast or slow that is, homotropic effect. When something else is bonding that affects that equilibrium, we call it a heterotropic effect. All right, I want to look at one other model, the sequential model that can account for allosteric effects. So before we looked at the concerted model, and we said in that model that our enzyme was either all in the T state, every subunit, and again, we've got 4 subunits in this one. You could have more or less for different enzymes, or all of them were in the R state. But in the sequential model, we see that this kind of conformation change happens a little bit step by step. So here we've got our enzyme in the T state, okay, and we get a substrate, S, comes in and bonds. And when that happens, that one subunit changes to the R state. But once the substrate binds, we see those neighboring subunits start to change. So notice I've got kind of a combination between my square and circle there. Okay, and so what we see is those neighboring subunits become slightly more active than the full square tent state, but they're not as active as they will be when they are fully in the R state. But now they're more likely to bond and become active, and so we see another one bond, and notice that our equilibrium is shifting more and more to the right as more and more of these bond. Right now this final one is kind of starting to get active and it bonds. And so we see this sequential model and we see our rate constants increase as we're going to the right. So this is another case in the sequential model where we're still talking about the T state and the R state. Okay, but we're looking at it in a little bit different way. And we will see these models and the effectors play out as we talk about metabolism later this semester. We'll look at this in lots and lots and lots of different cycles that we'll be studying.